In this video, I'm going to run through Topic 7, Magnetism and Electromagnetism of the Physics GCSE AQA specification. I hope you find it useful. We're going to start off by looking at a magnetic field. The region around a magnet where a force acts on another magnet or on a magnetic material is called a magnetic field. There are 4 different materials that can be magnetic. They're iron, steel, cobalt and nickel. Field lines, which you've got, if you look at this diagram here, going around there, they indicate both direction and magnitude, which is the strength or size of the magnetic field. If you have more field lines closer together, as we have got over here, that means that the magnetic field is stronger in that area. Whereas if we look over here, the field lines are further apart, that means that the field is weaker in that area. So the number of field lines in a given area indicate the strength of the magnetic field. The arrows that we've pointed on them here show the direction that the field is acting at that point. So you can see from here so far that the magnetic field is strongest at the poles, and it gets weaker the further away from the magnet that you go. The field lines, in terms of their direction, they show the direction that a north pole would move if it was placed in the field at that point. So you can see if we put a north pole near the north, it will be repelled and move away. And if we put a north pole near the south, it will be attracted and move towards the magnet. We can measure the strength of the field, and that's known as magnetic flux density, and that has the symbol B and the unit of Tesla. And you should be aware that a magnetic compass contains a small bar magnet, and because the Earth has a magnetic field, outside of the field of a permanent magnet, the compass needle points in the direction of the Earth's magnetic field. But if you were to place the compass in a magnetic field, the compass would align itself to the magnetic field of the permanent magnet. We're now moving on to look at magnetic induction. So a permanent magnet, such as the bar magnet down here, which is the north and the south pole, produces its own magnetic field. Whereas an induced magnet, such as this paperclip here, is a material that becomes a magnet when it's placed in a magnetic field, because a permanent magnet can induce temporary magnetism in a soft magnetic material. So if we were to bring the paperclips in, the paperclips will not be magnetic until they reach the permanent magnet. When they are attached to the permanent magnet or in the magnetic field of the permanent magnet, then they become magnetized, and then they behave like a magnet. So you can see here this top paperclip will get a north and a south pole, which means if we bring another paperclip close to it, again it will follow the pattern north and south. But if we were to remove this bar magnet, the permanent magnet, away from this situation, the paperclips would lose their magnetism very quickly and they would all fall down. So some key points about induced magnetism. Induced magnetism causes attraction, but it cannot cause repulsion. You can use repulsion to test if an object is a permanent magnet, because only permanent magnets will be able to repel one another. When the permanent magnet is removed from an induced magnet, the induced magnet will quickly lose its magnetism and will no longer be magnetic. We can now look at attraction and repulsion. So when 2 permanent magnets are brought close to one another, they exert a force on each other. The magnetic force is an example of a non-contact force. So it's a force that acts at a distance. The idea is that the magnets don't actually physically need to touch one another in order to exert that force. How they exert the force on one another is due to the magnetic field lines that go around the magnet. So the permanent magnets can exert a force on each other because the magnetic fields from each magnet interact with one another, and that causes either attraction or repulsion. You need to be aware that light poles will repel. So if we bring 2 norths together, they'll move apart, that's repulsion. If we bring 2 south poles together, they will also repel and move apart. But you should also be aware that opposite poles will attract. So if we bring north and south together, they'll attract. This causes the magnets to move towards each other. We've now completed looking at magnetism, so we're going to move on to look at electromagnetism. So when a current flows through a wire, a magnetic field is produced around the wire. The field depends on the size of the current and the distance from the wire. So what we've got here is, if you look at the screen, this picture down here, we can see that the current's flowing through here, and that's causing a magnetic field to flow around in that direction. If we want to know the direction of the magnetic field, we can use what we call the right hand screw rule, sometimes called the right hand grip rule, or a corkscrew or a pencil sharpener rule. And basically what you do is you use your right hand, this is in your right hand, you point your thumb upwards, and the thumb's pointing in the direction that the current's travelling in, and then your fingers are pointing in the direction that the field lines will go in for the magnetic field. So if you look at this diagram here, this shows a good example. So your thumb points in the direction of the current, and then we can see here that that magnetic field is going anti-clockwise. You could be expected to sketch on the magnetic field in the exam. On the previous slide, we had the magnetic field of a straight wire, so we could see that the magnetic field went round the straight wire. But if we were to shape the wire as a solenoid, which is a coil, as shown in the diagram here, and also in the diagram here, where we coil the wire around something, if we shape the wire as a solenoid, then that will increase the strength of the magnetic field. So shaping a wire to form a solenoid increases the strength of the magnetic field created by a current through the wire. The magnetic field inside a solenoid is strong and uniform, and the magnetic field around a solenoid has a similar shape to that of a bar magnet. So you can see here's our solenoid here, okay, where the current's passing round in the coils of wire. And what we then end up with is we end up with a north pole at this end and a south pole at this end. And you can see this shape of this field is very much like the shape of the bar magnet that we had on one of the first slides. Again, we can use the right hand grip rule here to find the direction that the north pole is. What we do with the right hand grip rule this time is our fingers go around in the direction the current is travelling around the wire, the coils of wire, and our right thumb points in the direction of the north pole. So you can see that for this setup here, the reason why we know the north and south is by using the right hand grip rule as we've got it here. Remember that in terms of the direction of the current, when we're looking at the current we assume always flows from positive to negative. Just to emphasise then the similarity between the two fields that you get in a solenoid, the magnetic field you get from a solenoid, and also a bar magnet, you can see the similarities here. So this is a bar magnet, again, with the field lines going out of north and going to south, and this is for a solenoid with the field lines going out this end and going in that direction as well. If you use the right hand grip rule, you can see that your thumb does point to north if you show the direction the current's going in. We can enhance the strength of a solenoid by placing an iron core inside a solenoid, and this is called an electromagnet. So an electromagnet is a solenoid with an iron core. Adding an iron core increases the strength of the magnetic field of a solenoid. And there's some other things that you need to know about how we can increase the strength of an electromagnet. So the strength of an electromagnet can be increased by increasing the current, increasing the number of turns of coil, or making sure that you use a core made of iron. And any of those three things, so the three things, current, coils and core, can all increase the strength of an electromagnet. Electromagnets can be used to produce very strong magnetic fields. So we're going to look at the motor effect. We've already looked at this in some detail, but in the motor effect, a force is produced when a current carrying wire experiences a magnetic field. The size of the force can be increased by increasing the strength of the magnetic field or increasing the size of the current. Now, we said before that a current carrying wire produces its own magnetic field, so the magnetic field that's produced by a current carrying wire interacts with the permanent magnetic field that's produced by the bar magnets. You can see over here we've got bar magnets. The currents produce a magnetic field, the bar magnets are producing a magnetic field, those fields interact, and that results in a force being exerted on the wire. In this case, the force is downwards. So the motor effect, again, just to reiterate, is a force is produced when a current carrying wire experiences a magnetic field. And we've said that the size of the force can be increased by increasing the strength of the magnetic field or increasing the size of the current. Some key points to just clarify this as well is the conductor will not experience a force if it is parallel to the magnetic field. And the direction of the force is reversed if either the direction of the current or the direction of the magnetic field is reversed. But if we were to reverse both the current and the direction of the magnetic field, then the force would stay the same. So if we want to know the direction that the force acts in, we can use Fleming's left-hand rule. So this time we're using our left hand rather than our right hand. And on our left hand, we want to make all our fingers be at 90 degrees to one another. So the thumb points in the direction of the thrust, which is the motion or the force that acts on the wire. The first finger points in the direction of the magnetic field. This points from north to south. The second finger is the conventional current, and that moves from positive to negative. So usually you'll be given the direction of the magnetic field, so you'll be given a south pole, and you point your first finger towards the south pole. And you would then point your second finger towards the negative terminal, and that will give you the direction the force will be travelling in. A key thing, again, just to get across with the motor effect, is when a current carrying wire is placed in a magnetic field, the magnet and the conductor exert a force on each other, and the direction of that force, as we've said already, can be determined using Fleming's left-hand rule. So the motor effect is such an important thing that we're just going to go through it one more time, so hopefully you'll definitely remember it. The motor effect is when a conductor carrying a current is placed in a magnetic field, the magnet producing the field and the conductor both exert a force on each other. We've already gone through Fleming's left-hand rule, but that's shown again on this side, so where the force is represented by the thumb, the magnetic field is represented by the first finger, which points towards the south pole, remember, and the current which is the second finger, which points from positive to negative, and that shows you the direction the force would act in. Now, if we wanted to calculate the size of the force, we can use an equation. So for a conductor at right angles to a magnetic field, carrying a current, the force can be calculated using the equation F equals B times IL, or F equals Bill, where F is force measured in newtons, B is the magnetic flux density, which is measured in teslas, I is the current, which is measured in amps, and L is the length, which is measured in meters. The size of the force exerted on the conductor by the magnetic field can be increased by increasing the strength of the magnetic field, by increasing the current through the wire, or by increasing the length of the wire that cuts the magnetic field. And when I say cut the magnetic field, I mean the length of the wire needs to be passing through the magnetic field. It's no good having a really long wire and a very small region that passes through the magnetic field. It's the length of the wire that's actually inside the magnetic field. And again, that should be 90 degrees to the magnetic field in order for it to get the full extent of the force. So now I'm going to look at some applications of the motor effect. And one of the main applications is getting an electric motor, which is shown in this diagram over here. Okay, so how do we get the electric motor to work? So a coil of wire carrying a current in a magnetic field tends to rotate. So you can see rather than just having a straight line of wire, we've got the wire coming in this way, the current's going to go around here and then come back this way. Now what that means is that the current on either side that's at 90 degrees to the magnetic field, so that's this side and this side, will experience a force but in the opposite direction. And so a coil of wire carrying a current in a magnetic field tends to rotate. This is because the current passing around the coil travels in the same direction around the coil. But as the coil bends, the force experienced on the different sides of the coil are in the opposite directions. This causes the coil to rotate. Now, one of the key features of an electric motor is this bit here, which we call a split ring commutator, and that reverses the current around the coil every half turn. And the reason it wants to reverse the current around the coil every half turn of the coil is to ensure that the motor keeps spinning in the same direction. So you can see that as this rotates up to the top, if we had the current still going that direction, it would still have force going up. But the split ring commutator allows the current to flow in the opposite direction, which means that this now gets a force going down and continues in the same direction in terms of its rotation. So we've now reached the end of the content that's on the combined science paper. Any content after this slide is for the triple students only. So if you're a combined science student, thank you very much for listening. I hope you found this presentation very useful. If you're a triple student, I'm afraid we've got a few more slides, so please keep listening, and I hope you find the next part just as useful as the first half. Thank you. So the first part of the triple only content is loudspeakers. Loudspeakers are an application of the motor effect. I'm going to look at these in a little bit of detail. On this side of the screen you've got a diagram which shows how a loudspeaker is set up. So you can see the electrical current goes in here, it goes around this coil of wire, and you've got a permanent magnet, and the coil is also connected to a cone, and the cone allows for some vibrations. So how the loudspeakers work then? The current in the electric circuit is varying because the current is alternating, so we supply a loudspeaker with alternating current. The current passes through the coil, which induces a magnetic field. The magnetic field of the coil, as the current passes through it, interacts with the magnetic field of the permanent magnet, which is around the outside. That causes the coil to experience a force, so it's either going to move in or it's going to move out. When the current reverses direction, and it will reverse direction, remember, because it's alternating current, that causes the force to change direction. That causes the coil to move in and out, causing the coil to vibrate, and in turn, that vibrates the paper cone that transmits sound waves. So as the cone vibrates, this causes the air molecules to bunch together, forming compressions, and then spread apart from one another, causing rarefactions. This pressure variations are the sound waves which then propagate through space. So key things about a loudspeaker, just to emphasise the key points that we really covered here, is you need to use alternating current. Remember that changes many times per second. The alternating current flows around the coil. When a current flows in the coil, it produces a magnetic field. That magnetic field interacts with the magnetic field of the permanent magnet, and then those two magnetic fields exert a force on each other. This causes the coil to move. Now, because we've got alternating current, the force changes direction many times per second, and that causes vibrations that lead to sound waves being produced. We're now going to look at a new principle, which is called electromagnetic induction. Electromagnetic induction is the reverse of the motor effect. And with the motor effect, remember, we were using an electric current and a magnetic field to produce a force, which causes something to spin. Now what we're going to do is going to use a force pushing a conductor in a magnetic field, and that is going to produce a current. So if an electrical conductor cuts through a magnetic field, which means it passes through a magnetic field at right angles to the magnetic field, a potential difference is induced across the ends of the conductor. If a magnet is moved into a coil of wire, a potential difference is induced across the ends of the coil. Now, if the conductor is part of a complete circuit, a current is induced in the conductor. So if you look at this diagram at the bottom, we can see if we move this wire in and out of this magnetic field, we'll get a current being induced, or a potential difference being read by this meter. In the same way that if we force this magnetic field through this coil of wire, we'd end up with the voltmeter would flick to the right to begin with, and then as the magnet fell through, it would end up flicking to the left. The key thing that you need to know about the induced current is an induced current generates a magnetic field that opposes the original change. So it opposes the change that created it. And how it will do that is that either the movement of the conductor or the change of magnetic field will be in the opposite direction. So an application of the electromagnetic induction are alternators or AC generators. We've got a diagram of an alternator or an AC generator over here. And we've also got the output in terms of potential difference graph with regards to time. So how do they work? The coil of wire is rotated in a magnetic field, so this time we're applying a force to cause this to rotate round. Okay, so we're spinning them round inside the magnetic field. You can see the coils of wire go around here, they're the conductor. So as we spin this in the magnetic field, we're causing the conductor to cut the magnetic field, and that induces a potential difference across these ends. So as the conductor moves through the magnetic field lines, a potential difference is induced across the coil. This causes a current to flow. As the coil is connected to slip rings, which are over here, there is a continuous contact. This causes a potential difference in current to change direction every half turn, so we get an alternating current being produced. Now you need to know that when the coil is parallel to the magnetic field, there's no potential difference induced, and when the coil is perpendicular to the magnetic field, a maximum potential difference is induced. So you can see at this graph here at the bottom, it's showing we've got alternating current because we've got it in the positive direction and then in the negative direction. So if we were to look at one full turn of the coil, you can see that it would start off and as it begins to turn up to 90 degrees, when it's at 90 degrees you get a maximum potential difference. It would then begin to fall as it went back to 180, so it was parallel with the magnetic field. And it would then rise as it went down to 270, where it becomes perpendicular with the magnetic field again. And then after one complete cycle, it would be back to being in the parallel position again, which is where it started. So key things to take away from this is that now we're using a force to spin a conductor inside the magnetic field. That induces a potential difference across the ends of the conductor, and that causes an alternating current to flow. It's an alternating current because it's in continuous contact with this slip rings. You also need to be aware that you get a maximum potential difference when the conductor is at 90 degrees relative to the magnetic field, and when the conductor is parallel to the magnetic field, so in line with it or at 0 degrees, you get no current or no potential difference flowing through the conductor. Another application of the generator effect is a dynamo or direct current generator. A dynamo is a direct current generator. It works in almost exactly the same way as an alternating current generator, except a dynamo has a split ring commutator instead of the slip rings. That means that every half turn the connection is swapped. As a result, we end up with direct current being produced and not alternating current. So you can see over here, we've got the graph of the dynamo. Now, if we remember from a previous slide, our AC generator would go like this, it would go up, and then it would come down on this dotted line. But for a dynamo, what happens here is that the connections are swapped rather than staying continuous, which means that the current continues to flow in the same direction and causes direct current to be produced. But it still has the cycle, so that's one complete cycle. Now, for both AC and DC generators, the potential difference can be increased by any one of these things. So by increasing the rate of rotation, increasing the strength of the magnetic field, or increasing the number of turns of coil that's on our conductor that's cutting the magnetic field. We're now moving on to look at microphones. Microphones work like loudspeakers but in reverse. So a moving coil microphone consists of a coil of wire wrapped around one pole of a magnet. Above and below this coil are the opposite ends of the magnet. So sound waves cause the coil of wire to move relative to the magnet and the magnetic field. As we've got a moving conductor next to inside a magnetic field, that causes a potential difference to be induced across the ends of the coil. The induced potential difference causes a current to flow through the circuit. Because the coil is vibrating with the vibration sounds of someone speaking or singing, that causes the movement to oscillate. And so the conductor will move in one direction one moment and then move backwards in the opposite direction again in the next moment. This vibrating is constantly changing direction, which causes an induced potential difference and current to alternate, producing AC or alternating current. A louder sound will cause the coil to move more and therefore induce a larger current. Now the electrical signal produced matches the sound wave, so if you speak more loudly you get a larger movement of the coil, which means that you get a larger potential difference being induced, which leads to a larger current. And so the current, the spikes in the current, the size of the current, and also the frequency of the current match the sound waves that we use to produce it. So the last thing we're going to look at in this topic are transformers. We've got 3 slides on transformers to go through. So this is the first of 3. So you remember from paper 1 that transformers can either be step-up transformers, in which they would have more turns of coil on the secondary coil here, or they can be step-down transformers, which would have more turns of coil on the primary coil. So you can see we've got more turns of coil on the primary coil, less turns on the secondary. This makes this a step-down transformer. So our potential difference is going to increase from the primary voltage will be greater than the secondary voltage. We get a decrease in current because it's a step-down transformer. Now in paper 2 you need to be able to explain how these transformers work, and how they work is in the following explanations. So an alternating current travels into the primary coil, so an alternating current travels through here, and you should remember that an alternating current is going to produce a changing magnetic field. That changing magnetic field runs through the primary coil and into the iron core. So you've got a changing magnetic field in the iron core. Because the iron core is linked to the secondary coil, we now have a changing magnetic field running through the secondary coil. A changing magnetic field in the secondary coil is going to induce an alternating potential difference across the ends of the coil, and that's going to cause an alternating current to flow around the wire or the conductor. Because we've got less coils on this side, that means the potential difference is going to be less over here, and that's going to cause the potential difference to decrease. But it will increase the current because power remains constant, remember, and power is equal to current times potential difference. So if potential difference goes down, current must go up in order to keep the same power. Just to make sure we're fully aware of how transformers work, we've got an example of a step-up and a step-down transformer. So the top one here is a step-up transformer. We've got less coils on the primary, more coils on the secondary. A step-up transformer, the potential difference across the secondary coil is greater than the potential difference across the primary coil, but the current is decreased. And remember, we use these to make energy transfer through the national grid more efficient, because the lower the current, the less chance of collisions, so the less heat is lost as the current is transferred through the national grid. A step-down transformer is shown in the bottom part here, so you've got more turns of coil there, small numbers of coil there, and a step-down transformer, the potential difference across the secondary coil is less, but the current will be greater. And we use step-down transformers, remember, to make electricity safe before it enters our homes. So you also need to be able to calculate things using transformer calculations. There's 2 equations you need to be aware of. The first one is shown here, so the potential difference across the primary and secondary coils of a transformer are related by the equation Vp over Vs is equal to Np over Ns, where Vp is the potential difference on the primary coil, Vs is the potential difference across the secondary coil, Np is the number of turns on the primary coil, and Ns is the number of turns on the secondary coil. And you use that equation in order to carry out calculations. Transformers are brilliant. We can assume them to be about 100% efficient, and the electrical power output would equal the electrical power input because of this, because they're 100% efficient. So the power output on the primary coil is equal to the power output on the secondary coil. We know that electrical power is equal to current times potential difference, so we can substitute that equation in. So we can now see the potential difference across the primary coil multiplied by the current passing through the primary coil is going to equal the potential difference across the secondary coil multiplied by the current running through the secondary coil. And again, that's another equation that you need to use to carry out calculations for transformers. That brings me to the end of the PowerPoint presentation. I hope you found it useful in preparing for your exams, and I wish you the best of luck in your exams and in the future.